In this video, I want to introduce how to determine the molecular formula from the empirical formula. So in the previous video, when I first introduced the empirical formula, we looked at the following compounds. So we said that there's a molecule where it has the molecular formula of C6H12, right? Cyclohexane, that has this molecular formula. And we know that its empirical formula, because of this 2-to-1 ratio between the hydrogens and carbons, would be CH2, right? And so we know that if we wanted to get the molecular formula from this empirical formula, we would just multiply all of this by 6, right? So you multiply by 6, you got 6 carbons, you got 12 hydrogens, that's your molecular formula. But how do you actually figure out how to go from this empirical formula to this molecular formula? How will we determine that we need to multiply by 6? Well, the key is the molar mass of the molecule, right? If you can determine the molar mass of the molecule, you can figure out your molecular formula from the empirical formula. So let's take these two, this molecule as an example. So the molar mass for C6H12 is going to be 84.16 AMU, right? So that's our molar mass for cyclohexane. Now, what we can do here in order to establish the difference between our empirical formula, our smallest ratio, and the actual molecular formula is to calculate something called the formula mass. So formula mass. So formula mass is really just a general term, calculating the mass of any chemical formula that you're given. But in this particular case, we're using it to say this is the mass of our empirical formula, right? So if we were to calculate a mass for this empirical formula, we take the atomic mass of carbon and 2 times the atomic mass of hydrogen. That's going to give us 14.026 AMU as our formula mass for this empirical formula. Now, what you'll notice is, okay, so there's a multiple of 6 that separates this formula from the molecular formula. There's also a multiple of 6 that separates this formula mass from the molecular mass, right? So if we multiply 14.026 AMU times 6, that's going to give you 84.16 AMU, right? So basically, in order to determine the molecular formula, all you need to do is first determine your empirical formula, calculate a formula mass for that empirical formula, then establish a ratio between that formula mass and your molecular mass, right? So let's look at a different example. Let's actually use the molecule that we looked at in the previous video. So the empirical formula that we got from the last problem in the previous video was CH3O. Right? We were given some mass percent data. We, went through some calculations and we were able to deduce that the empirical formula for that compound in the problem was CH3O. So when we have this empirical formula, let's say we were to take that same compound, do a mass spec, and get the total molecular mass. So let's say that the total molar mass for our compound is equal to 62.07 AMU, right? So let's say this is our total molar mass. We want to figure out what's the molecular formula given this empirical formula and this total molar mass, right? So that means that the first thing that we want to do is calculate the formula mass. So we're going to calculate the formula mass. And I want to go through this in detail. It's the exact same thing as calculating the molar mass for a molecule, but we'll go through it in detail. So you got 1 carbon in this empirical formula. You have 1 carbon, right? So that's going to be 1 times 12.01 AMU, right? Obviously, that's going to give you 12.01 AMU. You got 3 hydrogens here, so we're going to multiply the atomic mass of hydrogen by 3. So 3 times 1.008 AMU. That's going to be equal to 3.02 AMU. And you're going to have 1 oxygen in this empirical formula. So you got 1 times 16 AMU. And that's obviously going to give you 16 AMU. Right? So again, this is coming from our empirical formula, right? Just 1 carbon, 3 hydrogens, 1 oxygen. So our formula mass is going to be 31.03 AMU. Again, this is our formula mass. The mass for our empirical formula, right, is 31.03 AMU. So in order to establish the difference between the molecule that produced this molar mass and our formula mass is just to divide them, right? So we determine a ratio between the formula mass and the molar mass. So we'll have our molar mass divided by the formula mass. So in this case, that's going to be 62.07 AMU divided by 31.03 AMU. So that gives you a ratio of 2, right? So this molar mass is twice as large as our formula mass. So what does that mean for us in determining the molecular formula? What that means is that we're going to have to multiply this empirical formula by 2 in order to get the final molecular formula. So if we do that, we end up with a molecular formula of C2H6O2. Right? So that gives us our molecular formula from the empirical formula. All we had to do was just calculate this formula mass, right? Okay, so let's go through an entire example where we determine an empirical formula, we're given a molar mass, and we want to know what is the molecular formula, right? So this problem, and also one issue that students struggle with a lot is when they end up with these non-integer ratios when getting the empirical formula. So this example is going to cover all of that. So the example says cadaverine is a foul-smelling substance produced by the action of bacteria on meat. It contains 58.55% carbon, 13.81% hydrogen, and 27.40% nitrogen by mass. Its molar mass is 102.2 grams per mole. Determine the empirical formula and the molecular formula of cadaverine. Right? So the first thing that we want to do here, we have all of our mass percentages, right? The first thing we want to do is determine the empirical formula, right? And so in order to do that, we want to get the number of moles that are present in a particular sample of cadaverine, right? So again, like we did in the last video, the first thing that we're going to do is assume 100 grams of total compound. So if we assume 100 grams of our total compound, again, that just makes the math easier for us. That means that we can take these percentages and turn them directly into masses, right? So for the carbon, we know that in a 100 gram sample, we'll have 58.55 grams of carbon, right? Going off the periodic table, we'll have for every 1 mole of carbon, we have 12.01 grams of carbon. So that means in a 100 gram sample, we will have 4.88 moles of carbon present in cadaverine. Now the next one is hydrogen. So for hydrogen, we will have 13.81 grams of hydrogen in a 100 gram sample. Again, looking on a periodic table, have for every 1 mole of hydrogen, we'll have 1.008 grams of hydrogen. And so that's going to give you 13.70 moles of hydrogen, right? And lastly, we have our nitrogen present there. So we have 27.40 grams of nitrogen. And again, consulting the periodic table, for every 1 mole of nitrogen, we'll have 14.01 grams of nitrogen. So then that leaves us with 1.96 moles of nitrogen. Okay, so again, we have established all of our atoms here as the number of moles that are present in a 100-gram sample. So the next thing to do here is divide by the lowest number of moles, right? So we're going to divide by lowest number of moles, right? And in this case, that's going to be our nitrogen, right? So this guy is going to be our lowest number of moles that's present. So basically, we're going to just divide each one by 1.96. So starting with the nitrogen, to start with the easiest one, right? We know we got 1.96 moles of nitrogen. We're dividing by 1.96 moles. And so obviously that gives us a 1 for nitrogen. Okay, so now let's do hydrogen next. So hydrogen is 13.70 moles of hydrogen, and we're dividing by 1.96. So now this is going to give you a decimal. You'll get 6.99 for hydrogen, right? Now, in this case, if you get a number that's 6.99, 6.98 or something like that, that's extremely close to a whole number, you can safely round up this number. So this 6.99, we can go ahead and call that guy 7 for hydrogen. That's a safe round, right? If you're within 0.01, 0.02 of the number, that's a safe round. Now let's look at for carbon. So carbon is the last one we have here. So we got 4.88 moles of carbon. We're dividing by 1.96 moles, right? Moles. So when you divide here, you end up with 2.5 for carbon, right? Now, if you round this to 3, you'll be committing a mathematical cardinal sin. You cannot safely round this number up or down to anything, right? It's 2.5. It's in the middle of 2 and 3. We can't round that guy like we could round this one, right? It wouldn't be, safe mathematically to call this 3. So what we end up with from just directly these calculations is an empirical formula that looks like this: C2.5 H7N. Now, we cannot leave this in this form, right? Why is that? Because this flies in the face of Dalton's atomic theory, right? We can't just have these non-integer whole number ratios, right? Atoms are supposed to be countable. They're supposed to be, countable whole numbers. So we can't have this C2.5 just outlying here. But easily, we can fix this, right? So if we just multiply everything by 2, right, then we can eliminate this decimal, right? If we multiply everything by 2, then we end up with the following, right? So we multiply all this stuff by 2, we'll have C5 H14 N2. And this would be the proper empirical formula. Right? Because it doesn't say, the smallest ratio period, including decimals. It says the smallest whole number ratio. So this is the smallest possible whole number ratio for cadaverine. Okay, now if we calculate a formula mass, I won't go through the details of the calculation because hopefully you guys have gotten, how to calculate these masses at this point. But if you calculate the formula mass for this empirical formula, you get a formula mass of 102.2 AMU. And if you check out our problem, that's actually the exact same as the molar mass for cadaverine. So what does that mean? That means that this formula is our empirical formula and it's our molecular formula. Right? It's the smallest whole number ratio and it is the actual composition for the atoms in cadaverine. So this will happen sometimes. You'll calculate an empirical formula, you'll get a smallest whole number ratio, and then you'll figure out that your formula mass is the same as the molar mass. That's perfectly fine. That just means that the empirical formula you have is the same as your molecular formula. It is the smallest whole number ratio possible for cadaverine. Okay, so hopefully you have a good understanding of the empirical formula and how to get the information of the molecular formula from the empirical formula. This is going to be very useful for being able to identify compounds in chemistry.